Johnny's having some issues, but it looks like we're recording, so I will get started. Yeah, so I wanted to talk today about mineralogy and the planetary implications of serpentinization on Earth, so terrestrial serpentinization, as well as serpentinization on Mars. And yeah, so I'm Ben Tutolo. I'm an associate professor at the University of Calgary. Long before I was here at the University of Calgary, I was a grad student at the University of Minnesota with my good friend Johnny down here. This is us ice fishing back in 2012 in this picture. So we were, we were fishing. And so I'm very glad, and I want to be, thank you very much for the invitation to give this talk today. And Johnny, of course, will always be a good friend of mine. Okay, so I'm going to talk today about serpentinization. So this serpentinization reaction, we'll walk through exactly what that means and what that is. But one of the biggest implications of the serpentinization reaction is that life thrives at the interface, so that place between where serpentinization fluids are created and emitted into seawater. So they contain hydrogen, hydrocarbons, and they have generally a fairly alkaline pH, and seawater. And so in that area where they mix, we see lots of active microbial ecosystems. This is from the Lost City hydrothermal field on the Mid-Atlantic Ridge. Here in the middle is the fossil system at the Iberian margin. So we see, again, abundant evidence for ancient life that used to live there. And then there is some evidence that on the Saturnian moon of Enceladus, that there are serpentinization reactions that could also contain life as well. Importantly, and this is going to be part of what I talk about today, is that these gases that could be produced directly from serpentinization reactions like hydrogen, or as a result of other carbon reduction that happens in the presence of these reducing fluids, these gases can be potent greenhouse gases, and they could help to warm the surface of early planets. So serpentinization, what actually is it? It's a common planetary process. Basically anywhere you have water and olivine at fairly low temperatures, you're going to make serpentine minerals and magnetite. So the first step is that serpentinization adds water to olivine. Subsequently, it's going to oxidize iron and produce hydrogen. But we can start with a rock like here on the left-hand side, mantle peridotite, a nice dunite, as we would call this one here. We can add to it a significant amount of water. So this is a large beaker of water, 1.3 liters of water added to a kilogram of rock or so. And we end up with this rock on the right-hand side, which is a serpentinite. And it contains, again, about 13% water by weight. So we start with a nominally anhydrous rock here on the left-hand side, this dunite. We added water to it, and on the right-hand side, we end up with this serpentinite. And that serpentinite contains minerals like serpentine and brucite, as well as magnetite. And in the process, we've oxidized iron and produced hydrogen. So we can really explore that process using geochemistry. I know this is sort of the Earth data webinar, so we can talk about the geochemistry more specifically. So this is a plot of oxidized iron over total iron as a function of loss on ignition or H2O weight percent on the x-axis. And we can see a general trend of them increasing diagonally across the page. But I'm going to show a series of these plots, and when we look at them, the best way to think about them is that going from left to right, we're increasing the degree of serpentinization, where we're starting from 0% serpentinized to 100% serpentinized when we end up with the water content of about the mineral lizardite, or LZ here. And then on the y-axis, we need to think about that as iron oxidation and coupled hydrogen generation. So we start with basically no oxidized iron in the protolith serpentinite or peridotite, and we end up with significant amounts of oxidized iron in the serpentinized rock. So again, we're starting with a dunite, this beautiful olivine-rich rock on the left-hand side, adding to that water, and in the process making the serpentine and magnetite minerals that you see in these veins here, as well as hydrogen gas. We could take that same plot, and instead of having it normalized by total iron, we could actually just calculate or just report the measurements of oxidized iron weight percent on the y-axis. And in that case, we can assume that the initial peridotite or olivine was 100% ferrous iron, so all Fe2+, And as it was serpentinized, we make Fe3+. In so doing, we can then convert iron weight percent to the number of moles of hydrogen per kilogram of rock that regenerated. This is going to be important as we go on here. So yeah, this hydrogen gas is generated, on a fairly steep trajectory here, or steady trajectory as we serpentinize the rock. And so on the modern Earth today, serpentinization is a globally significant source of hydrogen. So this is a global map of hydrothermal vents around Earth that have been identified. And so if we go and then take all of these vents and sum the amount of hydrogen that's being generated on Earth today, we end up with this table that was brought together by Barbara Sherwood-Waller back in 2014. And so what we see is that there are these different estimates for the oceanic crust, but if you really focus on the slow spreading ridges, the places where mantle peridotite will come into contact with seawater, we see that that number is as much as or higher than the total sum of hydrogen production over the entire oceanic crust, meaning that, again, serpentinization is a globally significant source of hydrogen on the modern Earth. So if we want to then think about the way that serpentinization would have looked on the early Earth versus the way it looks on the Earth today, we might have to use our imaginations a little bit. So this figure here is from a very good children's book called When Planet Earth Was New. And this is, in the book, it walks through basically Earth's history. And this is the page that is dedicated to the origin of life on Earth. And so what I really, really like about this book is it basically just says life began in the oceans, and it allows the reader or the children who are reading it to imagine how life initially began. So many folks hypothesize that in the early oceans, serpentinization locations, so places where hydrogen-rich fluids are interacting with seawater, would have been a prime place to originate life. And so what I want to talk about and think about is our understanding of serpentinization-driven hydrogen fluxes and hypotheses based around the origin of life in serpentinizing systems, are they biased by our modern experience? We have this very nice survey of the global hydrogen fluxes coming from serpentinizing systems today, but would that have been different in deep time? And so this is a research question that I explored as part of a project with my former PhD supervisor, Bill Seafried, and my postdoc supervisor, Nick Tosca. So, but to really get at this question, we first need to understand the mineralogical mechanism for how hydrogen is generated during low temperature serpentinization. So there's a really nice paper by Friedrich Klein. The title speaks for itself: Magnetite and seawater serpentinite, some like it hot. So essentially, the take-home message from this paper is that if you're serpentinizing peridotite at temperatures lower than around 200 degrees Celsius, you do not make magnetite. Rather, you end up with minerals like brucite in your rock. And so the difference here is, again, this really bright phase in the backscatter electron imagery is the mineral magnetite. Magnetite, of course, has oxidized iron in it. It's 2/3 oxidized, 1/3 reduced iron. But if you're serpentinizing olivine at lower temperatures, that oxidized iron must be accommodated in a different way in order to produce hydrogen. And the really important reason why we would want to focus on low temperature serpentinization is this is where the origin of life would have been thought to have occurred. And the highest temperature limit of known life today is about 121 degrees Celsius. So we really need to focus on these low temperature reactions to think about life's origins if it did occur in serpentinizing systems. So this is, again, borne out in geochemical models of the serpentinization reaction. So on the right-hand side, we have the mineral olivine here. So above temperatures of about 350 degrees or so, olivine is thermodynamically stable in the presence of water, so no serpentinization reactions happen. But as we drop through its window, where it no longer is stable, we end up with minerals like brucite, serpentine, and magnetite. And you see there's a narrow window over which magnetite will actually form as a result of serpentinization. That's from about 250 to 350 degrees. And then below that, and certainly below 200 degrees Celsius, models predict that there is no more generation of magnetite, and therefore serpentine must be the primary way in which oxidized iron is generated. So again, to dive even deeper into the mineralogy of these serpentinization reactions, we can look at this crystallographic diagram of the mineral lizardite. So lizardite is the most common form of serpentine that forms in seawater serpentinites. we can see that this is alternating layers of silica tetrahedra and magnesium octahedra. And so what happens is that somehow oxidized iron must be incorporated into the serpentine during this reaction in order to generate hydrogen, because again, we're not making magnetite. This can happen in one of three ways. The first is dioctahedral substitution. We're substituting in 2 oxidized irons for 3 magnesiums, and we're ending up with a vacancy in the crystal structure. This makes a mineral known as hissenderite. This will become even more important when I talk about Mars later on in the talk. But suffice it to say that we did some work on this back in 2019 with Bernard Evans, looking at how this reaction actually happens. So this can form a very nice solid solution with oxidized or with lizardite and hissenderite. The second potential mechanism is deprotonation. So essentially what happens there is you're popping off an OH group from the serpentine structure and while putting in a magnesium or an oxidized iron. And this makes something called oxyserpentine. I have drawn into question the potential for this reaction actually happening in nature. I think that perhaps this data set that proves that it, or that claims to prove that it is a dominant mechanism for iron substitution might be biased by the sample preparation techniques. So I'm sort of disregarding that as a potential mechanism for hydrogen generation. And then the third, and the one that I'm going to focus on the most for reasons you'll see in a minute, is this what's called Ferri-Chermak substitution. And this is a coupled substitution of 1 oxidized iron into the tetrahedral sheet and 1 oxidized iron into the octahedral sheet for a magnesium and a silicon. So again, you're going 6 for 6 in charge, so you're maintaining charge balance. But we end up with a mineral or solid solution with this mineral, magnesium constantite. So again, you still have magnesium in the octahedral sheet, but you've had to pop off one of those silicons in order to make this oxidized iron substitution happen, this coupled Ferri-Chermak substitution. So if we want to investigate the dominant mechanism for oxidized iron substitution to serpentine, we need a way of probing both the oxidation state, so how much of the iron in the serpentine mineral is in fact oxidized, and also its coordination state. Is it in the tetrahedral sheet or is it in the octahedral sheet? And to do that, we can use a technique known as Mossbauer spectroscopy, which is really fantastic. We're probing the coordination and oxidation state of iron in serpentine mineral structures. And this is actually the one that flew on the original MER rovers that flew in the early 2000s onto Mars. So this actually was an instrument measuring oxidation states of iron on Mars for some period of time. And again, it's using the radioactive decay of 57 cobalt in order to probe the oxidation and coordination state of 57 iron. If we assume that that 57 iron is representative of all of the iron in the sample, then we have a very good idea of the oxidation and coordination state of that iron. If I go and then collect all of the varied analyses of oxidized iron, or Mossbauer analyses of oxidized iron coordination and oxidation state in serpentine minerals, so I end up with a total of 68 analyses, individual analyses, 23 of which are specific to the mineral lizardite, 33 of which are specific to the mineral chrysotile, and some that are ambiguous as to what the actual end member serpentine is in them. What we see actually is that within error, all of these analyses, the average of them, gives us approximately 0.5 tetrahedral over total iron. What does that mean? That means that Ferri-Chermak substitution, that coupled substitution of oxidized iron into the tetrahedral sheet and oxidized iron into the octahedral sheet for a magnesium and a silicon, must be the dominant mode of ferric iron substitution. And we can take this a step further and go and do very precise electron microprobe analyses of all of the 3+ cations that occur in serpentines. So this also includes elements like aluminum that might also participate in Chermak's type substitution. What we see is that the abundance of oxidized iron and aluminum and any other 3+ cations increases linearly as the number of silicon atoms per Fermi unit decreases. What does that mean? That means in order to generate oxidized iron, we must be incorporating less silicon in the serpentine structure. And that has strong implications for what the activity of silica in aqueous solutions will do to the generation potential of, or to the hydrogen generation potential of serpentinizing systems. So again, exactly what's happening there is that we're plugging in an oxidized iron for a magnesium in the octahedral sheet and an oxidized iron for a silicon in the tetrahedral sheet. And again, the really important thing is that we need, or this is favored by, low activities of aqueous silica. So if we do an analysis again of how much hydrogen you can generate through this Ferri-Chermak substitution, we end up with a diagram like this, where the most hydrogen is generated, again, at the lowest number of silicon atoms per formula unit down here in this section of the diagram. So what we can now start to think about is that, okay, if hydrothermal processes would have happened in the early oceans and the silicon concentration in early Earth seawater might have been quite different than it is today, then we might have ended up with very different hydrogen fluxes from these systems. So how might actually these secular changes in seawater silica concentrations have affected hydrogen production during serpentinization on early Earth? So this is just a schematic diagram of the way in which biology has dramatically changed the silicon concentrations of seawater over geologic time. Early on in Earth's history, 4 billion years ago or so, there was no biological limitation on silicon. There was nothing in seawater making its skeleton out of silicon. So the concentration of silicon in seawater was really only limited by the solubility of amorphous silicon. And so that's about 2 millimoles per kilogram at ambient temperatures. Gradually through time, around the beginning of the Phanerozoic era and in Neoproterozoic time, we start to have sponges and radiolaria that are starting to soak up that silicon from seawater and suck down the amount or the concentrations of silicon in seawater. And then about a quarter of a billion years ago or so, diatoms evolved and really became very efficient at soaking up all of the silicon in seawater, such that the modern concentrations of silicon in seawater are around 100 micromolars or so, down from 2 millimoles early on in Earth's history. So can we actually now do something with this knowledge about the fact that silicon concentration has changed over geologic time and that silicon activity will affect hydrogen production? Can we predict actually how the hydrogen fluxes would have changed? So to do that, we can use this new tool that we published in Chemical Geology earlier this year, known as PyGeoChemCalc. What this can do is we can take electron microprobe analysis of a mineral like serpentine, which you see here. So we have your typical cation-anion distribution. We can take that and turn that into a mineralogical formula. In this case, it's just a simple Ferri-Chermak substituted silicon, or actually this one's just a greenolite lizardite solid solution. And we end up with what then becomes useful for predicting thermodynamic properties, things like the Gibbs free energy, the enthalpy, entropy, volume, and heat capacity of that mineral. Using that data, we can then plug that in again to PyGC, a different module, but PyGCC can then calculate the thermodynamic properties and the solubility constants for serpentine as a function of, for example, temperature and pressure, as shown here. So this is formatted for the Geochemist Workbench software package, but PyGCC is an open source package that can be used to generate thermodynamic data and thermodynamic databases for many popular geochemical modeling software. So armed with now the knowledge that silica concentrations changed over geologic time, that the hydrogen production in serpentinizing systems depends strongly on the silicon concentrations in serpentinizing fluids like seawater, we can now start to calculate the quantitative changes in hydrogen fluxes from serpentinizing systems over geological time. So I can set up this equilibrium reaction. So between that reduced iron serpentine and oxidized iron serpentine. And then we end up with a seesaw function here, where if we decrease the silica activity, we will increase the hydrogen activity, and vice versa. If we decrease the hydrogen activity, we will increase silicon activity. If we assume that silicon activity is the main driver of this process, which is consistent with the fact that silicon activity is coming in with the inflowing seawater solutions and hydrogen is being produced, then we can calculate the relationship between the activity of hydrogen and the activity of silica, and compare that between modern oceans, where we have about 100 micromolars of silicon in seawater, and the ancient oceans, the Precambrian oceans, where we would have been closer to amorphous silica saturation. The take-home message here is that Precambrian serpentinites would have produced around 2.5 orders of magnitude less hydrogen than modern serpentinites, and that's really quite a profound difference. And this has important implications for the ability of these systems to warm the early Earth, as well as the ability of these systems to originate life. So we can end up with this new revised model for the ways in which hydrogen fluxes have changed through time. And so I've just now put this in as a fraction of modern, again, assuming that there is a direct and straightforward relationship between hydrogen and silicon activity. We can have this schematic model for the fact that hydrogen fluxes would have been significantly lower on the early Earth than they are today. And they would have changed as those creatures change the activity of silicon in seawater. And so those that might be skeptical of such a reaction or such an important role of silicon would need to look no further than, for example, the silicified komatiite from the 3.3 billion-year-old Mendon Formation in South Africa. So in this rock, this is a komatiite that erupted on the ancient ocean floor. And so these minerals or these crystals here used to be entirely composed of the mineral olivine. And now they are completely composed of the mineral quartz. So what this tells us is that ancient seawater would have had strong and continued interaction with olivine-rich rocks. Of course, this is a complete end member scenario where now instead of considering hydrogen generation, we're actually looking at a rock that has been entirely silicified, but you can imagine intermediate states where this hydrogen fluxes would have been reduced. And you might also be wondering about the kinetics of this reaction and whether actually the silica in ambient seawater would have been entirely soaked up during the serpentinization process. So here is an example of an experiment that we did actually still whenever I was at the University of Minnesota and published a couple of years later that shows that once you begin to make serpentine in a serpentinizing system, the reaction kinetics actually slow down quite dramatically. This is a reaction with aqueous silica and the mineral brucite, and it shows that once you sort of armor and turn the surfaces of your brucite into serpentine minerals, the reaction rate becomes so slow that you can actually see silicon activities persist through a hydrothermal system that would have been circulating silica-rich seawater. Okay. So that's the story for the ancient Earth that we were able to come up with by combining mineralogical and crystallographic observations with thermodynamic calculations. Importantly, though, not all olivines are created equal. So Earth's mantle, of course, has about 90% forsterite and 10% phaelite end member, but rocks like this one, like this palisite meteorite, many of us will have seen in gem shops or in museums, have olivine that is much, much richer in the phaelite end member than the terrestrial mantle, than Earth's mantle. And so because of that, not all serpentinization reactions are going to produce the same amount of hydrogen. So if we want to think about hydrogen production on other planets and moons in our solar system, we really need to start thinking about serpentinizing rocks that are quite different from Earth's mantle. So here's an example of a serpentinized troctolite from the mid-Atlantic ridge on Earth. So here is that serpentinized olivine crisscrossed by serpentine veins, and here's a plagioclase that's crisscrossed by chlorite veins. If we then compare that to a similarly serpentinized troctolite rock from the Duluth complex of Minnesota and USA, we can immediately see the strikingly different composition of those serpentine minerals. The serpentine minerals in this Duluth complex example are all brownish in color because they contain so much more iron than their terrestrial counterpart. And so that becomes very important for the hydrogen fluxes during this reaction, and we can walk through that step by step. Sorry for seems to be some sort of arrow down the middle of the page there, but the important thing from this slide is that the Duluth complex of Minnesota, which has these oxides, is much more iron rich than Earth's mantle, actually tends to compare quite well to compositions of Martian meteorites, bulk compositions of Martian meteorites plotted here as well. So if we want to study serpentinization of the Martian crust and serpentinization on Mars, we really need to think about iron-rich rocks like those of the Duluth complex, and I will walk through that here in a second as well. So here is a plot of the solid solution between phaelite or iron-rich olivine or iron end member olivine and forsterite or magnesium end member olivine. And what we see is a terrestrial mantle, it plots very close to the forsterite end member. So here, down here is forsterite, so magnesium silicon oxide. So that's the dominant magnesian end member of olivine. And up here is phthalate, so the iron end member of olivine. And we can then do just a calculation of the ideal solid solution between forsterite and phthalate to end up with this curve here. So we see the terrestrial mantle plots very close to forsterite. How do Martian olivines compare to those from the terrestrial mantle? We can then go and use, for example, analyses returned by the Curiosity rover in Gale Crater on Mars to get an idea of this. So the Curiosity rover has on board an X-ray diffraction instrument known as the CheMin instrument. So it's able to drill samples, scoop them up, and put them into its belly, and then scan them using X-ray diffraction. Then using that return data, we can do a Rietveld refinement to determine exactly what the iron composition is of the olivine in the analyzed sample. With that data, so now Curiosity has analyzed a total of 4 geologic samples that had olivines in them. We can see that these rocks, these olivines on Mars and Gale Crater are significantly more iron rich. They plot significantly closer to that phthalate end member than the forsterite end member, and certainly than the terrestrial mantle. They are all around 4 to 5 times more rich in iron than the terrestrial mantle. We can then go and collect all of the electron microprobe analyses of olivines in Martian meteorites, and we see that we end up with 2 populations there. One is the olivine poor basaltic shergottites and clinopyroxenites plotted here. So those are olivine poor rocks, so those probably wouldn't be the subject of serpentinization reactions. If we look specifically at the olivine rich rocks, so for example, the olivine orthopyroxene ferric layersolitic shergottites and dunites, we can see that they plot very consistently with those Gale Crater olivines, and in all cases are very significantly more rich in iron than Earth's mantle. So if we want to understand how hydrogen would have been generated and how a hydrogen greenhouse might have operated on early Mars, we must study anomalous serpentinites on Earth. We must study rocks that look like these olivine-rich shergottites and dunites. Fortunately, the Duluth complex has olivines that plot rate overlapping with the Gale Crater olivines. So importantly, these olivines are rare or very distinct from the terrestrial mantle, the most abundant reservoir of olivine on Earth's surface today, or on Earth today. They're much more iron rich than that rock, or than the mantle, and therefore they must be doing different reactions whenever they're becoming serpentinized. And so we need to study serpentinites of places like the Duluth complex of the United States in order to quantify this reaction. So there is abundant outcrop of this Duluth complex, these olivine-rich layers of the Duluth complex, and those the trochrolitic series. And they specifically outcrop right there in the city of Duluth, or right south of the city of Duluth. And those are rocks that I was able to sample while I was still a PhD student. I've been back a number of times since in the intervening time. So again, if we look at these plots of the generation of oxidized iron over total iron as a function of serpentinization reactions, or again, the generation of hydrogen in terms of just the total concentration of oxidized iron in these rocks, we can start to think of, or we can start to have something to compare against when we're thinking of the serpentinization of the Martian mantle. So now what I've done is I've taken all of those plots, those points from the previous page, and turned them gray, so they're in the background now. And I've plotted the ferric over total iron for a bunch of analyses of rocks from the Duluth complex. And what we see is that, as my high school history teacher used to say, the more things change, the more they stay the same. Actually, this trajectory of generating oxidized iron as a fraction of total iron with increasing serpentinization is actually quite the same as it would be if we were serpentinizing the terrestrial mantle. But if we then go and calculate and plot the total oxidized iron concentration as a function of hydrogen or water weight percent, we see that these Duluth complex serpentinites are generating so much more hydrogen than the typical terrestrial mantle serpentinites, approximately 5 times more for any given degree in any given degree of serpentinization. What that means is, even if a rock is only 20% serpentinized on Mars, it will have produced the same amount of hydrogen as a 100% serpentinized rock on Earth. And so the other thing that you might be noticing here is that these trajectories don't go towards the same place, right? A fully serpentinized terrestrial rock is about 13% water content, whereas a fully serpentinized Martian rock doesn't seem to be anywhere near that. And that's because the iron weight percent, or iron itself, weighs much more than magnesium. And so they actually plot to much lower degrees of total water weight percent as the degree of serpentinization progress. Again, what's happening here is hydrogen is being produced as magnetite and oxidized iron, or hissengerite, grow. And I'll show that how we know that here. So iron-rich serpentines can be distinguished by an electron microprobe. In this case, there's so much iron in the mineral structure that we can actually just make a diagram like this. What I've plotted here is the silicon over total cations, atoms, over the ratio, or versus the ratio of iron over iron plus magnesium. Magnesium serpentine, like glycerdite, plots down here in the total in the lower left-hand corner. Iron serpentine, iron 2 plus serpentine, or reduced iron serpentine, plots over here, mineral greenolite, and then hissengerite plots up here. And so what we see is this ratio of oxidized over total iron. As we follow these pathways, we end up with more and more hissengerite. If we go then and do a kernel density estimate of all of the analyses we have of oxidized iron or serpentinized rocks of the Duluth complex, so this is a total of 93 analyses, what we see is a trajectory clearly going towards hissengerite, a solid solution between the mineral magnesium serpentine, like glycerdite or chrysotile, greenolite, and hissengerite, and not this magnesium constantite that we would have seen before. If we had magnesium constantite, we would expect the silicon actually to be reducing as this reaction occurs, because again, that's a coupled substitution for the silica tetrahedra. We can also prove this another way, or we can examine this another way by examining the oxidation state of iron-rich serpentines using X-ray absorption near-edge spectroscopy. So what this allows us to do is plot a variogram of different iron end members. So we're only probing now the iron that's in the mineral structure between octahedrally coordinated iron 2 plus, octahedrally coordinated iron 3 plus, tetrahedrally coordinated iron 3 plus, and tetrahedrally coordinated iron 2 plus. This particular substitution would be totally impossible in the serpentine mineral structure. So if we were getting the magnesium constantite serpentinization substitution reaction that we get in serpentinization of the terrestrial mantle, we would expect a trajectory going towards approximately half oxidized iron in the tetrahedral sheet and half oxidized iron in the octahedral sheet. Whereas if we're getting hissengerite substitution, which is suggested by the electron microprobe data, we would expect to be going down along this trajectory towards the bottom here. And what do we see? We see exactly that. We see the production of this octahedrally coordinated iron 3 serpentine, or specifically hissengerite. So we see we're going from olivine or iron 2 rich serpentine, but mostly olivine, towards again oxidized iron in the octahedral sheet of serpentine. So we're making the mineral hissengerite. We can then go and again do Mossbauer spectroscopy on these rocks, and we see that the oxidized iron is being generated in a way that is very consistent with our bulk rock analyses of the oxidized iron content of these rocks. We also see that the oxidized iron that is attributable to this hissengerite versus magnetite is around half. So we're at the same time we're generating oxidized iron in the form of hissengerite, we're generating about an equal amount of oxidized iron in the form of magnetite. So bringing this all together, it means that even if Mars is only weakly serpentinized, serpentinization likely played a significant role in its biogeochemical evolution. This is a plot from Bethany Ellman from 2010, showing that the stars here are definitive identifications of serpentine, and black dots are places where they looked at the orbital spectroscopy data but did not find the mineral serpentine. And the white squares are places where serpentine was probable but not definitively defined. So what you see is that there's not very many stars on this page. So for those of us out there that study serpentinization reactions might be very disappointed by this plot, saying perhaps that there's not very much serpentine on Mars. But if we go and look, rather than looking for example, in this plot, they're looking for minerals like lizardite, antigrite, or chrysotile. If we look instead for hissengerite specifically, so all of these circles would be consistent with orbital identifications of the mineral hissengerite. And then the background here is the magnetic anomaly map showing areas of high magnetic anomalies. What we see, or we begin to see, is that hissengerite or hissengerite probable areas of the planet coincide roughly with the places where we have large amounts of magnetization, suggesting that a much larger role of serpentinization is actually possible than would have been initially thought based on those initial analyses of probable identifications of magnesian serpentines like lizardite and chrysotile by Bethany Ehlmann over a decade ago. So Mars used to be warm and wet. We know that from evidence that has been returned by all of the rovers and orbital spectroscopy and orbital imagery on Mars. We can see things like aqueous geomorphology features consistent with valley networks and crater degradation and basin lake formation. And we can also see that in geochemical and mineralogical signatures like clay minerals that must have been produced by water reaction with basaltic minerals on early Mars, as well as sulfates and evaporites and manganese oxides that really could have only occurred in the presence of water. So it used to be warm and wet, although that apparently stopped about 3.5 billion years ago. These are models from Wordsworth's paper from last year showing the production of the production of warm and wet conditions on Mars. And so depending on the carbon dioxide content of the atmosphere, the number of years, millions of years plotted on the y-axis, that the planet would have been warm enough to stabilize liquid water increases a little bit. But the CO2 is not the only part of the story. In fact, you need another reducing greenhouse gas like hydrogen in order to actually stabilize these warmish temperatures. And that's shown here. So this is the model for the amount of oxygen or hydrogen in the atmosphere at that time. And so the red is oxidizing environments and blue is reducing environments consistent with the production of hydrogen. So if serpentinization is producing a bunch of hydrogen on early Mars, it is stabilizing liquid water and keeping the planet warm. Ultimately, though, whenever we generate a big pulse of hydrogen through serpentinization reactions, that hydrogen quickly escapes space. Mars is a much smaller planet than Earth, so it's got much lower gravity, and it also has no magnetic field, and that makes its its outer atmosphere very easy to be stripped away by the solar wind. So ancient Mars experienced warmer and wetter conditions when these hydrogen generation reactions would have been happening because there was already a little bit of water being stabilized by perhaps CO2 on the early planet. But as you generate a pulse of hydrogen, that hydrogen is then rapidly stripped off to space. The escape rate of hydrogen from the atmosphere is proportional to the concentration of hydrogen in the atmosphere. But now Mars is cold and arid because ultimately those reactions ceased and there was no more hydrogen being generated. Okay, so that was a lot about serpentinization in a very short time. So just to give some take-home messages from the talk today. First is that hydrogen production during serpentinization is fundamentally controlled by the mineralogy of the serpentine and accessory minerals that you form. So low temperature serpentinization tends to produce magnesian kronstadtite on the modern Earth. If we had higher activities of silica in serpentinizing fluids on the early Earth, they would have produced less hydrogen because that coupling between the activity of silica and hydrogen generation that we showed thermodynamically. So this low temperature serpentinization in these silica-rich oceans would have produced orders of magnitude, so about 2.5 orders of magnitude less hydrogen than their modern counterparts. That has important implications for the potential origin of life in ancient hydrothermal vents, as well as the ability of hydrogen to warm the early Earth. But on Mars, because there's so much more iron in the protolith olivine, those rocks can produce a lot more hydrogen simply by the fact that they have more hydrogens. They would have produced at least or around 5 times more hydrogen than even the most iron-rich rocks in the terrestrial mantle. And these newly developed thermodynamic and kinetic tools, I only talked briefly about the kinetic experiments that we've been doing, but certainly the thermodynamic tools in the form of PyGeoChem software can help us to answer these fascinating and challenging questions about the history of both Earth and Mars. And I certainly encourage you to reach out if you'd like to learn more about the PyGeoChem tools that I presented today. So I want to thank everyone, not only for the invitation to give this talk to your university today, but also for giving me the chance to talk about one of my favorite subjects, which is serpentinization. And I'm happy to answer any questions if there are any. I am not hearing you, Johnny, unfortunately. But yeah, if anyone has any questions, feel free to turn on your mic and I will happily answer them.
Hi, Professor. This is Shichao.
Hi, how's it going?
Yeah, pretty good, thanks. So I just have a question about magnesium actually. So your presentation shows us the more substitution of of iron in the serpentine structure means a less magnesium in that structure. So on Earth, I think the magnesium can cooperate with the carbon dioxide to form the carbonates. So maybe something happened to the magnesium on Mars.
Yeah, that's a good question. I think that the striking lack of carbonates, especially magnesium carbonates on Mars, is an important mystery that we really need to think about in the history of serpentinization reactions on Mars. So we end up with lots of, for example, magnesium sulfate minerals, suggesting that magnesium was mobile on early Mars. But the fact that we don't see carbonate minerals suggests that we either have an alkalinity problem where the pH of the waters was too low, so you never made carbonates, or perhaps you don't have enough CO2 in the atmosphere to actually give you that amount of carbonates. So most of the models of early Mars that give you a warm and wet early Mars have significant amounts of CO2 in the atmosphere, suggesting that perhaps the reason that there's no carbonates might be because of fairly acidic solutions that were unable to precipitate carbonates. But I think the jury is still really out on the lack of magnesium carbonates on Mars.
Yes, thanks.
Thank you for that question. So there's a question in the chat. How do the below factors decide for the reaction of Archean hydrogen production? Temperature, hotter Archean ocean, oxidized iron and serpentine, lower in Archean, and silicon and Archean water. So temperature will affect everything the same. And by that, I mean that you will produce more hydrogen with increasing temperature, but the silica effect is the same. And so the question of where hydrogen is actually made in serpentinizing systems, it isn't made at 25 degrees Celsius or even 2 degrees Celsius of the bottom ocean. In fact, it's made deeper in the system, probably at 150 or 200 degrees Celsius. So in all cases, those reactions would have undergone, or serpentinization reactions would have happened at fairly elevated temperatures, no matter what the temperature of the ambient seawater is. And there's a good indication from the silicified chromatiates of the Barberton group that, in fact, those reactions probably happened at about 150 to 200 degrees Celsius, same as they do on the modern Earth. So the oxidized iron in serpentine would have occurred less than on the modern Earth due to this activity of silica effect. So again, serpentinization reactions that produce hydrogen are all thought to occur around 150 to 200 degrees Celsius. If you have higher activity of silica, you produce less oxidized iron through the Ferri-Chermak substitution. And that specifically occurs because you're mostly making the mineral lizardite, right? So most of the magnesium from olivine is dissolving and reprecipitating as the mineral lizardite. And then you have that 10% of wiggle room to produce oxidized iron in the serpentine structure, which is then up for grabs in terms of how much silica you have attending that reaction. And the factors about silicon in Archean water are simply based on the thermodynamic constraints we have on the solubility of silica minerals. If there are no organisms sucking silica out of seawater, there is every reason to believe that the silica in the ocean waters on early Earth would have been only limited by amorphous silica saturation. They would just build up until you precipitate amorphous silica. And that is borne out by our examples of Archean bedded cherts or deep water cherts on the early Earth. So we see sedimentary rocks that don't look anything like cherts we see on the modern Earth. And that's because of that much higher activity of silica in the ancient seawater. So thank you very much for that question.
So, but what happened to the serpentine polymorphic? For example, I think the lower temperature serpentinization can produce a crystal, and the distillate is only may favor to be formed when the alumina is present.
Yeah,
so that means, yeah.
Yeah, certainly. You can, no matter which mineral that we're looking at, if you're serpentinizing FO90, the terrestrial mantle, it seems like the dominant mode of oxidized iron substitution into that mineral structure is ferri-Chermak substitution. So a coupled substitution of oxidized iron into the tetrahedral and octahedral sheets. So regardless of the dominant polymorph, whether it's lizardite, chrysotile, or even antigerite, this mechanism that depends on the activity of silica is dominating the production of hydrogen.
Okay.
Thank you. Yeah, if there's any other participants that have any questions, I'm happy to answer. It couldn't have been that clear. Okay, well, if there aren't any more questions, then I want to thank you all again for inviting me and for coming out to the talk today. I hope to maybe someday visit you there in China. That'd be lovely. And I hope to see you all at some future meeting. Thanks, everyone. Have a nice day. So long. Have a nice day. Bye.